All right, welcome back to System Software. So today we're continuing looking at how we compile our simple IR language and how we can represent higher level languages like this intermediate representation in assembly. So last time we started on pointers, and we're going to continue today looking at the other two pointer operations. But first, questions about pointers, questions about what we went over last time, questions about Code Gen 1, which I think is due today. Oh, no, sorry. Let's do next time. Not to scare you. Sorry. Do next time. Questions about Code Gen 1? And I've released Code Gen 2. Oh, I released Code Gen 2 last time. So questions about Code Gen 1, Code Gen 2? Everybody good? Yeah.
Just confirming I remember what I'm supposed to be doing properly. We're taking basically simple IR and converting it to assembly, right?
That's, yep. Okay. Tried to kind of repeat that as many times as I could. This is the goal of the compiler. And it's easy to say that, but then when you go to actually do it, it can be a little confusing because your temptation is to start evaluating the language. Like you see 1 plus 2 and you're like, well, the answer should be 3. But the job of the compiler is not to tell you what the answer is, it's just to put it into a different language, express it in a different language. Kind of analogous to a human translator, translating human languages. So we're not trying to interpret the meaning or the result of the program, we're just trying to produce it in another language. And as you can start seeing, what makes that hard is that the input language has many, many possible ways to run, has many possible inputs and outputs for sufficiently large programs. And we have to not just think about what one program means, but how to translate any program. So what is the general pattern of addition look like? What does the general pattern of operations look like? And how do we generate that in an equivalent assembly program? Yeah? No, we won't be doing a linker in this class. Maybe if you take OS, they might do that as an exercise. But no, we won't have to do a linker in this class. We're just going to do language translation for the system, for this compiler-related system tool. Other questions on Code Gen 1 and Code Gen 2? Questions on pointers from last time? All right, let's do the homework. So the question was, if a variable has an offset of -24 from the base pointer, write x86-64 assembly code that will result in the address of x being stored in register RAX. So we want the address of x. So this is what operator in simple IR? Or in C, it has the same name. Reference, yeah, reference. Or I think maybe C is address of. But the reference operator. All right, so this is directly answered in the notes. So how do we do that? So what's the assembly code, like kind of pseudo assembly code? What's it kind of look like to get the address of x being stored in RAX if x has an offset of -24? What are the operations? One set of operations to accomplish that. Anyone want to take a chance testing your knowledge? Yeah.
I think you can move RBX into RAX and then shift RAX to
Okay, that's getting there. So it's taking, well, we don't want to take RBX, take RBP, which is maybe what you meant. That's the base pointer, is RBP. So yeah, we want to copy that. Let me get some scratch here. So yeah, we want to, so kind of the algorithm here is we want to take RBX and let's move it into a temporary register. We don't want to overwrite RBP. And then let's shift or change RBP somehow. So what we can do is we can subtract from it. So we can take RAX and subtract 24 from it, or add -24, however you want to frame it. Okay, so now does RAX So now what does RAX hold at this point? It's the address of X, right? So if you want to like load from X, what was the assembly to load? If you want to load X into RAX, or let's say RBX to avoid conflicts. So the way you would do that in assembly would be to use this memory indirect or register indirect offset addressing. This is how you would do it. But the architecture is doing this computation for us. These instructions here, they are the sequence of assembly instructions that we need to run in order to perform the same computation that the architecture is computing under the hood. So yeah, I think this is the answer, right? So move RBP into RAX, and then subtract 24 from RAX. And now RAX holds the address of X. Yeah? The difference between, say, you mean like this move and this move?
No, using the instruction load effective memory.
Oh, yeah. So there is another instruction that you can use to do this.
Is it the same thing?
Let me look up the. So there's a. So what was it? Load effective. This one, LEA.
And you use a cube from 86.
Yeah, you can use this to do the same thing. You can use this to do the same thing as what we did here. So if you choose to use that, that's fine. You can do that. Store effective address for M. Address for. Yeah, you can do this as well. This is also possible to do this. But it's another operation to learn. So I did it using the fewer number of operations that we know. But yeah, if you it probably shows the pseudocode here of what it does. Bless you. Oh yeah, so it has. So there's another function, effective address, which is defined somewhere else. But he's just showing that you can do this. I think it would just be like this, right? You just do this. Yeah, you can just do that to get the address. But
It would be how the key would be.
oh, what?
LEA and
LEA. Oh, you're saying it would be you'd have to do the 64-bit one. Okay.
Yeah.
Okay. Yeah, that would do the same thing. Excuse me. Is there another question? I see someone there. Okay. But don't worry about that. It's just another instruction. But this is kind of more explicit. Shows the two steps. You get the address of RVP, subtract 24 from it. All right, other questions on the homework? All right, let's do attendance. Okay, so let's get back into pointers. So just a quick refresher, we had three operations. One was reference, where we get the address of a variable. We just went over that in homework. We have dereference, where we look up the value of a variable. We take the address and follow that address to find the value at the address given by T1. And dereference assignment, where we take some value and we store it at the address given by a variable. Questions on these three operations? They're like identical to the C operations. Okay, so we did this full example last time. Showed how you could use this diagrammatic approach to show pointers. But we also went over the kind of architectural mental model of this, something close to the architecture where we have addresses and memory slots, the values at those addresses. And we looked at how the state of the machine changes after each one of these after each one of these pointer operations, after each one of these operations in simple IR. Okay, questions about this program? So what value of x gets returned by this program?
Okay.
So I heard 8, I heard 11. Who says 8?
No, no, that's
Who says 11? Because it's a pointer, right? So we've got x equals 8. We get the address of 8 in T1, and then a dereference assignment of T1, which T1 points to x's address. So when we do a dereference assignment of T1, it changes the value of the memory address that x is referring to. Yeah, so it's 11. Bless you. And remember that at the architecture level, there's this was the diagrammatic view, the kind of machine mental model view. There's nothing about T1 that says it's a pointer. There's nothing in the value of 88 that distinguishes it from a pointer or a floating point or an integer. The only reason that it gets treated as a pointer is because of where's that code? It gets treated as a pointer because the operation that the developer asked for. So it's really the operations that define, at least in part, define what data types are. It's not just the data values, it's also the operations on those values. So an integer is not just a sequence of integer values, or like, a 2's complement, or whatever representation is being used. It's also the operations that you can perform on it. So that's what distinguishes pointers from integers, is that you have pointer operations versus integer operations on them. Okay, questions on this example? The meaning of these pointer operations, what they look like from this low-level mental model of the machine. Everybody good on these? Okay, so just quick review. For reference, we introduced this new, that wasn't for reference. So for reference, we did what we did in class. We computed the address by taking RBP, which is the memory address of the symbol table, or memory address of the variables for the local variables. So this is what the symbol table looks like. It's all offsets from RBP. We saw this, again here, bless you, in memory. RBP has the address of the starting point of these local variables. It's like the local variables are kind of like an array in memory. For our compiler, they're an array in memory. And then local variables are allocated to offsets of these local variables. Any questions on that? We covered this a couple of times, but I just want to make sure that that part is clear. That RBP is the special register that holds the address of the local variables. And each local variable is at defined offset from that address. So in order to get the address of a variable, one way to do it, it's not the only way, one way to do it is to start with that address of the local variables, store it in a register, and then just add the offset to it. Generate an instruction that adds the offset to it. And then save that address into the destination variable. So in this case, we had, what was our instructions? We wanted to take the address of x and save it as the value for T1. X has address offset -32 from RBP. T1 has offset -48 from RBP. So the code we generate to perform that reference operation subtracts 32 from whatever RBP is, and then stores that result in offset 48 from RBP. Questions? Questions about that? Okay. All right, so let's look at dereferencing a pointer. What the assembly code looks like and how we can generate that assembly code. Okay, so how can we load a value from an address? We saw something like this in when we're dealing with variables. But what assembly instruction loads values from an address? Or what's the opcode that we used before for that? Any guesses? Everyone too afraid to guess? Is it add? Think about the ops we saw before. Move, yeah, it's just move. And there's a special mode of move called register indirect addressing. And we saw this when we were trying to get an offset from RBP. That was actually a variation of a simpler operation, which is just this register indirect move. So this parentheses is like asterisk in C. This is saying don't copy the value of RAX, but copy the value of the address that RAX holds. So let me get my whiteboard up. Let's do it this way. Okay, so if I've got if I have this snippet of code and my machine has this state, let's say I've got this is my RAM, and these are my registers. How does the state of this machine change with these two operations? So this first operation, what changes in my machine? So here's my RAM, here's my registers. How does the state of this machine change for this first operation? Yeah, RAX has value 100. And then for the next operation, how does the state of the machine change? Yeah, RBX will now have 100 in it. So what if instead I say this operation, and let's put some values in memory here. How will the state of the machine change after this third instruction, move parentheses RAX into RBX? It'll put 1 into RBX. Why? Why 1 into RBX? Because this register indirect mode says don't get the value of RAX and copy it into RBX. It says take whatever this value is, treat it as an address, and do a memory load from that address. So at address 100, in my sloppily written 100, address 100 has the value 1, so RBX will now get the value 1. So these have the same opcode in x86. They're both called move opcode. But under the hood, they're very different operations. One is a register copy, and one is actually a memory load. So in the MIPS world, those would be two different operations, right? There'd be load versus, what is it, copy or move or something. But here, the operand determines, in part, what opcode you're using. So this is going to be a register indirect load. Questions on that? That kind of makes sense? So putting parentheses around it denotes a memory load at whatever address is given in the register. Questions? Questions on this? All right. Okay, so that's the register indirect move. So our goal here is to do a pointer dereference operation. So how might this assembly code look? What might this assembly code look like? Let's see if we can try to do this together. So let's say we've got T2 equals T1. I think I forget the symbol table for it. Let me get the symbol table for it. So T1 is negative 48, and T2 is negative 56. So that's my symbol table. So what might the assembly code look like for this instruction? So we're trying to do T2 equals the dereference of T1, knowing that we have this memory, this register indirect addressing. What might the assembly code look like for doing this?
Is it one line?
What's that?
Is it just one line?
The way I did it was several lines. So we could work backwards. So how do we store a value into T2? Let's say we have the value we want already in T2 or in RAX. Let me see how I actually did this. Yeah, so you would move. Oops, sorry, I'm jumping all over. Oh, sorry, I'm jumping all over the place. Yeah, so we can say move. Let's say we had it in RBX. Move into the offset for T2, which is negative 56 from RBP. So this takes our ARBX into the variable T2. Pretty familiar, right? We've looked at this several times. So that's the last step of this. So what would we need to do before this? So if this were just assignment, if we were just doing T2 equals T1, then we'd still have this step here. We'd say like move RAX. But as a first step, what would we do if this were just T2 equals T1? We just reverse this, right? We take whatever T1 was, the address of T1, and copy that into RAX. So we can start the same way here. But how will this differ for dereference? Yeah.
I have a question on
Yeah.
that. Why can't we just do both those in one instead of having the RAX?
Oh, I see what you're saying. Why can't this be one instruction?
Yeah.
The architecture will only do a single memory load or store per instruction. It won't do two. It'll do, yeah. What's that? Yeah, it's like a limitation of the architecture. It'll do one load or store at a time, one memory operation at a time. Which is one reason why, you need compilers to go to the architecture for the architectural limitations. Okay, so this is how you do T2 equals T1. What's different? It's got to be different, right, for dereference. What's going to be different here? What do we have to do here? So we have the value of T1 in RAX, and we want to move some value. So what should RBX be? What do we want to have in RBX here? Okay, so if we have the address of T1 in here, that would be the same thing as T2 equals T1, because the T1, the value of T1, whether it's an address or not, is irrelevant to the architecture. This would just do a copy between the two memory locations. Whereas here, we want the value of the address that T1 holds. So RAX is going to be the value of T1, which is an address. So, now RAX has T1. T1 is some address, and then we want to dereference that address. We want to get the value at the address that's stored in RAX. So what operation do we use to get the value of an address given by a register? The parentheses, yeah. So we do this register indirect addressing to take the value of RAX, use that as the address for our memory load, and store that value from memory into RBX. Questions on that? Does that make sense? So it's very similar to copying between two variables, except here we're not trying to copy the value of T1 into T2. We're taking that value and then looking it up in memory. And whatever the value at that memory location is what we want to store into T2. Okay. So that's our register and direct move. So these are the 3 steps that we just went over. So get the value of the dereft variable, the variable that's going to be dereft. Get the value of memory at that address, and then store that value of memory, store the value of that memory at that address into the destination. So yeah, this is just going to be the same code. So take the value of the dereft variable T1. I switched RBX and RAX, but it doesn't matter here. Get the value in the memory address that's in RAX, and then save that into T2. All right, let me show this. Questions on this?
So
Yeah.
the second move with the parentheses, that's doing like the value, like what value it's pointing to, basically.
Yeah. If you think of RAX as a pointer, then this is like dereferencing the pointer in assembly. But remember, there's no notion of something being a pointer or not in assembly. RAX is just a register that can store any 64-bit binary value. It's when we generate an assembly instruction that does this register indirect, that's what imposes this address type on it. All right, so let me do this diagrammatically as well. So let's do this with an example to illustrate what's going on here. So let's take our memory. So let's say again, RBP is at 120, and let's say we've got offset -48 and offset -56. Now I have to do arithmetic. So 120 minus 48 sounds really hard. I think that's 82. Is that right? Am I this bad? No, 72. Am I this bad at math? Yes, I think I am. And then 64. Is that right? Did I get this math right? So this is T1, this is T2. And we've got our RBP register, which has value 120. That's just an example. At runtime, at compile time, we won't know what the value is. We've got register RAX, register RBX, and let's say we've got some values in this memory already. Bless you. We'll just put 11 and 12 here. All right, so let's say this is the state of our machine. This is what memory looks like at address 72 and 64, which are offsets from RBP. This is offset 48. This is offset 56. So these are the offsets. These are the vars, and this is the actual address. So RBP holds 120. There's some data in memory, and the values of our AX and RBX don't really matter. We could just say they're 0. They're going to be overwritten by this. Okay, so let's do the first operation. This is how we load a variable from memory that has offset -48. We just sort of memorize this. This is going to take whatever RBP is, subtract 48, which is T1, and it's going to give us that value from 11. So 11 is the value. This is going to be stored in RAX. Actually, you know what I should have done? Sorry, let me set this up slightly differently. So let me make it closer to the example we actually have. So let's put an address. This is like closer to the real example that we had. So I'm going to put the value 88 in here to start with. and I'm going to say 88 had value 11. Okay, let me start again. So we've got negative 48 here. Negative 48 is our offset of our value. That's going to be stored into RAX. So now RAX has value 88. And this next instruction is going to be a register indirect move. So it's going to take RAX and it's going to use that as the input to a load. So it's going to load from address 88, which has value 11, and it's going to save that value into RBX. With me so far on this? Make sense? And then we're going to take that value RBX and store it into basically do a variable store into an offset from RBP, offset negative 56 from RBP. So that's going to overwrite this memory state with the value of RBP. Questions on that? So we do our variable load, which is an indirect register indirect load as an offset from RBP. That's going to be this value here, and save that into RAX. And then we're going to use register indirect addressing again to take whatever the value of RAX is, use it as a memory address, and load that value into RBX. That's the second instruction. And then finally, we're going to take RBX and store it into the memory location associated with T2 using this register indirect addressing again. Questions? Questions on this? Okay. So it gives you a super low-level view of how pointer operations work, but hopefully it makes pointers a little clearer, a little simpler. As soon as you just wrap your head around the fact that any memory location, any memory value or any register is just binary data, and its meaning really depends on the operations you use. If you understand the operations, the difference between a register copy, which just copies data between two registers, and a memory load or store, which copies between registers and memory, then the difference is just, all right, well, where do you get the address? You either hard code the address, like we do for global variables, or we get that address from a register. If we get that address from a register, that register is effectively a pointer because it has an address, and there are special operations for using that register as the address for a memory lookup. All right, so that's dereference. Let's look at dereference assignment. Okay, so here it's the same idea where T1 is an address, but we're going to store a value at that address instead of loading a value at that address. All right, so how can we? So if we have a register that has a value, or sorry, a register that has an address in it, how can we store to the memory location at that address? Well, it's the same operand that we saw before. We just put parentheses. But instead of it being the source of the move, it's the destination of the move. So we can use this register indirect addressing both as the source and the destination for our move instruction in the Intel world. So then doing this store is kind of like a combination of what we saw before. So this is what the pseudocode is going to look like. We first get the value of the variable. So T1 is storing some number. We're going to get that. We're going to get that value first. Wait, why does this look wrong? Okay, forget that part. That looks wrong to me. I don't know why it looks wrong. But all right, so we're going to get the value of the variable to deref, which is T1 here. We're going to get that value. So this is how we get the address of T1. And we're going to store that into a register. We're going to get the value of the right-hand side. That's what we're going to store into the address pointed to by T1. And then we're going to store that value into the address of T1 that T1 gives, which is in RAX at this point. And that's it. That's all we need to do. We need to get the address that T1 is pointing to, which is just its value, save it into a register, get whatever the right-hand side is, save that into RBX, and then take that value, that right-hand side value, and store it into the address given by T1. Questions on that? You mean skip this, just to move? Yeah, you definitely can. But like I recommend for all these operations, if you do it this way, where you always store into a register, your compiler code is going to be a lot simpler because you don't have to generate different code depending on whether this operand is a number or a variable. This instruction will be hard-coded. So actually I can show what that, let me show what that template looks like. So then when you're generating code for any dereference assignment, so if this is my destination variable and this is my operand, then the code template that your compiler can use to generate assembly code will just look like, get the, so I need a little table here, so offset equals the symbol table lookup for the destination, and the assembly operand is that, I can't remember what I called it in C++, but it's like get operand. So then the code template will just say, all right, give me the offset from RBP for our destination into RAX, take whatever the assembly operand is and store that in RBX, and then finally just do RBX, RAX. So the only thing that needs to change in this assignment is the offset and the operand, which is either going to be an immediate load or it's going to be that offset from RBP. And then this last line will be identical. You could write code that looks something like this, where you say, if operand is a constant, then you can kind of like save some instructions in your output by changing what your output looks like, and then say, otherwise use this template. But I find it simpler just to have a single code template for all variations of that statement, if possible. But yeah, so in this scheme, this is your template for dereference assignment. Other questions on this? Okay, that's the assembly code. All right, so let's do the full assembly example. Yeah, let me get this out of the. So it's a little bit long because there's a lot of comments. Well, this might be. Okay, so should I go through the do you want me to see? Do you want to see the full assembly like trace through the full assembly of this program? Yeah? Okay. All right, let's trade to the full assembly. So first let's see the translation of this entire program. So this stuff is our template. Let me get some syntax highlighting for this. All right, can anyone not read the text size? Is text size okay? All right, so let's look at this entire example. So this is all template code here. Actually, this is all template code. Yeah. So this is all template code above here. This is the code that you'll generate, and then the rest of this is template code that we'll see how to generate when we look at functions. I think this is the whole thing, right? Yeah, this is all the code. All right, so we've got our assignment. Well, let's just make these the actual instructions. So there's x equals 8. There's y equals 9. There's t1 equals reference of x. There's t2 equals dereference of t1. And then here's dereference assigned to t2. And finally, t3 assigned to x. So there are our operations. So for x equals 8, it's just like before, I have a really simple code template. You could absolutely generate a single instruction for this if you wanted. You could do move 8 to negative 32 RBP. You can absolutely do that if you like. I do this because the code template is very simple. Actually, this is enter assign. You don't even have to implement this. But if you wanted to like optimize it, you could do that. So this is given to you. This is enter assign. Same thing, y equals 9, that's enter assign. So we just immediate load 9 into RAX, and then we load RAX into the offset into memory from RBP for y. And here's our address of operation. So remember the address of, we started with RBP, we subtracted the offset, and then saved that computation, which is the address of x, into T2. So save address into T2, C1, sorry. Compute address of x, get address of base pointer. And here for our dereference load, we get the value of T1, load the address, load the T1 address into RBX, and then store RBX into T2. So this was our dereference load, where we first get the value of T1, put it into RAX, and then load from that memory location into RBX. So now RBX has the value of the address that T1's pointing to. Take that value and save it into T2. Questions on this? And here we have our dereference store, where again, we get the address of, well, instead we get the address of the destination variable. So T1 is our destination pointer. We get its address, like we did here. So that star T1 starts the same way, where we get the address of T1, or the value of T1, I should say. We get the second, the right-hand side, the operand, stored into RBX, and then we do a register indirect store. This is a register indirect load. This is a register indirect store into whatever the address RAX is. And then we have another assignment from T3 to X. Questions on the assembly code? Okay, let's do this, excuse me, at the machine level here. Bless you. Oh my God, why? Okay, let's get our memory here. So we've got X, Y, T1, T2, T3. X has offset negative 32. Y has offset negative 40. T1 has offset negative 48. Negative 56. Negative 64. Let's keep RBP at 120. And then with my very bad math, X will have 88, I think. And then 80, 72, 64, 56. And okay, let's do the state of our registers. So RBP has 120, and we're only using RAX and RBX. Okay, so let's step through how the state of the machine changes after each one of these instructions. Okay, so assigning X to 8. First instruction, immediate load of 8 into RAX. How does our machine change? RAX gets 8, right? RAX has state 8. And then we move RAX into negative 32 offset from RBP. So how does the state of our machine change with this instruction? Does register change? Does memory change? Neither, both? Memory changes, yeah. So this, we can just look up the offset from RBP here, but at runtime, if RBP is 120, then the actual address will be 88. So whatever is in RAX will then be stored into this offset corresponding to X. So RAX has 8, so it'll be stored, 8 will be stored into address 88. Same thing with the next two instructions. So we've got move 9 into RAX. So RAX gets overwritten with value 9. And then we have move RAX into offset of negative 40 from RBP. So that'll take this value and store it into here. So this is the offset negative 40 from RBP. RBP has 120 at runtime. So negative 40 from 120 is address 80. So this memory location gets the value 9. Okay, so now here's our address of operation. We say move RBP to RAX. How does the state of our machine change when we run this assembly instruction? So we're here. Registers change, memory change, neither, both. Registers, right? So what changes? That's right. So RBP gets copied into RAX. So now RAX has value 120. And then we do add negative 32 to RAX. So what happens to the state of the machine?
Register changes.
Which register? RAX, good. So it gets negative 32 subtracted from it, which gives us 88. And finally, we have move RAX into negative 48. We saw this several times already. So that will take this value that's in RAX and store it into address 72, because that's offset negative 48 from RBP. Questions so far on this? Everybody with me so far on this? What's happening at least the machine level? What's happening? So you can see the machine doesn't really care or know whether T1 is an address. It's just running these instructions. These instructions just make a copy between two registers. The fact that RBP is a special purpose register for us doesn't really matter to the machine. It's just going to copy RBP to RAX, do this arithmetic, and then store whatever that resulting value is into memory. From our perspective, we can see that we want this to be an address. That was like our goal. But if you just look at individual instructions, the machine doesn't really care or know about that. Okay, now we're doing a memory load here from address 48 into RAX. So how does the state of the machine change from this instruction? Registers change, memory changes, neither, both? Okay, how does the register change?
Complicating the value in the memory in the register.
So what's the new state of the machine? RAX will hold 88, right? Already holds 88. Notice that? Already holds 88. So this is a place where an optimizing compiler would actually be able to avoid this. So you can see here, this is not actually making any state change. We're copying 88 into memory and then loading 88 into RAX. The machine doesn't actually change its state at this point. It goes through the cycles of doing it, but it doesn't change its state. And that's where an optimizing compiler could help reduce the number of instructions doing this. But the state of the machine doesn't actually change here. So it's loading 88 into RAX. It already had 88. The machine will do it for you. The machine will not be like, hey, it's already there. The machine will actually do it for you. So an optimizing compiler will help remove those number of instructions. It'll go through the cycles of doing the instructions, but the state of the machine won't actually change. And okay, so here's one of our first new instruction. How does the state of the machine change after this instruction? So move parentheses RAX into RBX. How does the state of the machine change?
The value.
Okay, so the value of the address. So it takes 88. Its address is 88 because that's the value of RAX. And instead of loading or copying this value into RBX, it uses RAX as the address to do a load from. So what will be the resulting state change in this machine?
Register.
Yeah, well, specifically, what will the register hold? Which register, what will it hold?
8 in RBX.
Yeah, RBX will hold 8, right? Because RAX is address 88. This instruction is saying, take RAX and use that as the address for a load. So that's address 88. And we load the value 8 from that memory location and store it into RBX. Questions? Questions on this? Everybody following more or less? Okay, and then we have what we've seen a million times already, which is to store the value of RBX into the offset for R2. So we take RBX and save that into the offset for T2, so that updates this address to hold the value 8. All right, fine. Now we've got our dereference. Yeah.
So on the previous one, if RAX didn't have the parentheses, it will load 88 instead in RBX.
That's right, yeah. If there was no parentheses, it would just be a copy from RAX to RBX. The parentheses say, take RAX and use it as the address, or do a memory load from the address given by RAX. That's what the parentheses mean, the operand. So yeah, that's how it differs greatly from, say, like the copy of RBP to RAX, like this one. So this is at the assembly level, this is like a pointer operation in the x86 world. All right, other questions on that? All right, let's do our dereference assignment. So we take the value of T1, we take whatever this memory location is, so it's RBP is 120, so we take the offset of negative 48 from 120, which is 72. We take that and we load it into RAX. RAX already has that value, so again, we've got another optimization opportunity here. This is called register allocation. If we can associate a variable with a register, then we don't need to do any memory lookups. But for easy compilation, we always just do the load before we use a value. So we load 88 into RAX, it's already there. Then we do an immediate load of 11 into RBX. So that updates RBX to have 11. And then what is the result, how does the machine state change when we do move RBX into parentheses RAX? Do the registers change? Does memory change? Both? Neither? Memory, right. So what changes in memory when we do this instruction? Say again, 11 is what? Stored in X. So X has address 88. So RAX has value 88. So this is saying store RBX into the address given by RAX. RAX is 88 and RBX is 11. So we store 11 into the address 88. Good, good. So now the address that is associated with X gets updated to 11. That's our dereference assignment, right? That's why X changes its value. And we'll see when we actually go to use X, the effect of this. So this is just an assignment. We take whatever is in the address associated with X, which is negative 32 from RBP, and we store that into RAX. So how does it say the machine change? Well, RAX had 88 here before, but now 11 gets stored into RAX. And then we take RAX and we store it into the address associated with T3. And so finally, T3's address has the value 11. So that's how, even though there's no direct assignment to X, there's this dereference assignment to X's address. That's what causes the value of X to change when you use it later. Questions on this? Does that help a little bit, I hope, to see the actual steps of the pointer arithmetic? So, this is what's nice about programming. You can always kind of break things down to the very simple set of rules to figure out what's going on in the machine, even if it's hard to understand kind of like abstractly what the pointers are doing. But I find this, very elucidating for understanding what pointers are. They're really, really very, very simple. It's just literally being used as an address. The value doesn't matter so much because it's all just binary data. It's the fact that you're doing this register indirect lookup that makes it a pointer. That's also why if in C, you could set a pointer to any value you want, like 0 if you accidentally set it to 0, and you dereference it, you get this error. But what's really happening is you're trying to dereference address 0, and the machine protects address 0 because typically the operating system is stored there. If you were using like an embedded device or a small microprocessor, you may be able to write in address 0 accidentally, and then you wouldn't get a nice error. Your program would continue running, and it might be harder to debug. But yeah, that's all that's happening with addresses. It's just instead of moving between registers, the register value is being used in a memory load. And that's really all a pointer is. Questions? Questions on pointers and their implementation? Yeah.
So, you know how we sometimes hold just regular like integer values within the registers?
Yeah.
Is that why we're explicitly doing like the move negative 48 RBP to RX to make sure it holds an address before we reference it?
You mean like in like the case of this?
Yeah.
This is to make sure it holds whatever the value, let me take a better example. So here, our goal is one way to think of at least C-like languages is each variable is associated with a memory location. So when we do this initial move, that's getting the value. Like whenever you use a variable, this is how you get its value into a register. So in most architectures like x86, your operations, like your arithmetic operations, can only be formed on registers. You can't like add two memory locations together. You have to use a register. So this is kind of like defensive programming in a sense that we just always load, whenever we see a variable usage, we always load it into a register in anticipation that it'll be operated on by something in subsequent instructions. Does that kind of make sense at all? Because historically, I mean, this is changing a little bit today, but for the CPU, the registers are really the memory of the CPU. The memory, and that was like the original like microprocessors, that it just had onboard memory, which were the registers. As time went on, people added RAM. They added RAM, and it's like a separate chip and has a separate bus for accessing data from it. So it's not, well, these days there are like systems on chips where memory is like located with, like on the actual die, but it still uses a memory bus, uses a memory manager to go out and get that data. But the CPU circuitry does its operations on registers, not on memory. The only memory operations it does is to do fetch, load, and store on the memory. So registers are the like onboard memory for the CPU. So everything is like expected to happen in registers. Yeah, it's also much faster than going out to the bus to get data from memory. I think even with a system on a chip. Other questions on pointers? So let me quickly show you the code templates, because I think this is probably useful for each of these. So I think I showed this one already, but you can kind of back out the code template for each of these pieces. So this is like the operand offset and the destination offset. So this is the code template for reference, for the reference operation. The only things that'll change are the offset of the operand and the offset of the destination. Otherwise, you can always hard code the rest of this. You only need to generate one type of sequence of assembly instructions. For dereference load, we can kind of back out the template here again. We get the operand offset from RBP. We always load it into RAX. We always do a register indirect load from RAX into RBP, and we always move RBX into whatever the destination offset is from RBP. So your code, like the C++ code, will actually be very simple. You just hard code all of this except for these offsets. And that you just get from the symbol table lookup. And then finally, for the last one, dereference assignment. That template looks like this. You get the destination offset, get it from RBP, always load it into RAX, move whatever the operand is into RBX, and I've given you a function to generate that operand, which will check whether it's an integer or a variable, and then just always load RBX into register indirect RAX. So those are your code templates. Let me copy these into one spot, and I'll put these in the notes as well. But those are your 3 code templates. So actually the project, like understanding what's happening is hard, but the code will actually be pretty straightforward. Now, to debug it and understand what's happening, you need to understand the concept, the semantics, but this is all the code will look like. It's just these 3 templates for doing it. So that's why I have what look like sort of unnecessary operations, because I don't want to have to like check for different cases. I just want to have one template for one construct. And also because I know that an optimizing compiler will remove pointless seeming pointless seeming cases like this, where I'm moving RAX into the offset -48 and then moving that back into RAX. Totally unnecessary. But in order to actually do that in your compiler, you have to keep track of information between these 2 instructions. And it's not always the case that a reference will be followed by a dereference. It might be followed by an if statement. It might be followed by an assignment. And so trying to keep track of every combination of cases is really, really hard. So instead, the strategy is to create the simplest translation and then use post-processing steps to identify these optimization opportunities. That's the way like modern compilers work. I mean, if you just like sit down and think through, well, in this case, yes, I could make a more optimal output, but I need to support every single simple IR program, not just this one particular one. So that's what makes compiler writing hard. All right, questions on pointers. All right, enjoy. Hopefully pointers are a little clearer. And I don't think the crowd will be that bad, but hopefully you understand pointers a little bit better. And see you on Thursday.